let's talk about what transformers are and what they do. So we need to first talk about a little intuition, and then we're going to talk about how they're used practically. And we'll talk about two types of use, one for impedance matching and one for power distribution. The two most common real-world uses of these things. So here's the intuition. You've got a voltage source, and in general it's a phasor. And this looks like an inductor, but it's a brand new component. And despite the fact that it looks like an inductor, it does not behave as one. I'm going to purposefully draw a different number of coils on the left and right side. We call the left side the primary side. And think about the primary side is where the current goes into and out of. And then we've got the secondary side, which is somehow the current is transformed. So current in the primary, I'll call this I1, it very much behaves as any other circuit. It goes up here, through here, and back down here in a complete loop. And then the secondary, it does the same thing. In order for a transformer to work, it has to be connected to some load. And I'm going to represent that in general as a complex impedance. You might sometimes see a dot placed on the transformer. I don't want to get it. Physically, the way these things are made is it's truly an inductor on one side, and it behaves like an inductor when it's alone. But then there's another inductor that's placed right next to the first inductor, such that the magnetic field lines from the first go through the second. And all of a sudden, once that happens, they no longer behave like inductors at all. If you see these two little lines in the center, like I've drawn, that means it has an iron core. It means physically as you wrap these things. So that's one, that's our, say, our primary side. And then we could also make our secondary side. And to couple those B lines, those magnetic lines even stronger, you could drop down a magnetic core in the middle. So in 3 dimensions, that would look sort of like a cylinder being dropped down there. And that couples those lines even more carefully. And sometimes you'll see these little dots on the top. They just get in the way more than anything else. What that's saying is that if one is being wrapped clockwise, the other one is being counterclockwise, then your current directions in your primary and your secondary would be reversed. It's a small secondary point. We're not going to talk about that at all. Instead, I want you to see that we've got these two different windings, and you know that there's going to be this V1 across this first winding. And what's interesting is that we'll have a V2 along the second winding. And if there is a N1 coils on the first and N2 coils on the secondary winding, all we really care about is the ratio of those. I'll just define this number N2 over N1, secondary over primary, to be N. So the way that I've drawn it here, I have lots of coils on the secondary winding, just a few on the primary. So N2 will be bigger than N1, and so my N is going to be greater than 1. And if its N is greater than 1, then the voltage at the output is going to be greater than the voltage at the input. And in fact, that little equation that I just wrote is a equation that you should know. It only works for sinusoidal state circuits. This transformers do not work for DC. But if you've got this alternating current on your primary, it will create a constantly changing B field, magnetic field, which will induce a current in your secondary, which, if it's got more coils in the secondary, will increase the voltage. Now, what do you think it does to power? Can it increase power too?
So I'm just trying to think visually these coils on top of one another. So it's creating this magnetic field.
That's right.
And is this magnetic field going to be like discharged at some point? Like,
right.
They discharge them through capacitors.
So remember how we said it's sinusoidal steady state. So this magnetic field is going to be growing, and then it's going to be collapsing and growing and collapsing. And at 60 hertz, it would grow and collapse 60 times a second.
Right. So
it's a very dynamic thing, constantly changing. And you know that in power, we are less concerned with voltage at time and current at time, and more concerned about average power. So we're trying to see in general, what does it do on average?
So on average, if it's growing and collapse, sorry, go ahead.
And my question, just to be clear, is can this transformer somehow increase the amount of power? So if we had, there's a power 1 on this left side, it'd be the complex power would be V1 times the complex conjugate of I1. My question is, could it somehow increase the power on that secondary loop, or would it have to be the same or less than in the primary loop? Can you use a transformer to create power?
I mean, I want to say yes if that magnetic field is like discharging into that second loop there. And
so instantaneously, it can definitely.
So average now.
But average. Right. That's exactly right. So average, it can't. If you could create a transformer that on average increased power, you'd solve the world's energy needs. You just have a couple of batteries attached to a 555 timer to make it sinusoidal or changing, and you just add more and more transformers, and you have an arbitrary amount of power coming out of those AA batteries. So you can't do that. So somehow our power on the secondary has to be, if it's an ideal transformer, and most transformers actually are pretty darn close to ideal, they don't lose any power, so the power in the secondary has to be the same as the power in the primary. And so if your voltage goes up in the secondary, what has to happen to your current in your secondary?
The current will increase, I'm guessing.
Well, if your voltage increased and your current increased in your secondary, then your power would go way up.
So would current stay the same?
If your current stayed the same, but your voltage increased, what would happen to your power?
Then it would go up.
Also increase, but it can't, because we can't create power. So it
have to go down.
So it's got to go down. And so if little n is greater than 1, then your voltage goes up and your current goes down.
So
go on.
I was thinking like that makes sense. So the same way that you multiplied the voltage by a factor of n, which is the ratio between the number of coils. So because voltage increases, you're multiplying it by n. N is greater than 1, so it would be increasing that value of V2.
That's right.
Since n is greater than 1, putting in the denominator would be decreasing the current.
That's right. And your overall power would stay the same. If you multiplied those two things before and after, before it's I1 V1, and afterwards it's I2 V2. But when you multiply the right side, the n's cancel, 1 over n cancels with positive n, and you're left again with I1 V1. So power in equals power out. So the rules for this, for the ideal transformer, and we're only going to cover ideal ones. We could make it more realistic by putting in resistances in there. But the rules for the ideal transformer, there's just three. The first is that V2 is equal to n times V1. It goes up, assuming little n is bigger than 1. The current goes down and only works for sinusoids. So that's just a little aside.
in an ideal transformer, the secondary coil will always have more. The secondary inductor will always have more coils than the primary.
No, just the way that I've drawn it. Because you could just as well take this transformer, flip it upside down, and now drive your incoming voltage on what here is the secondary. You just relabel secondary is now primary, primary is now secondary, and now your N would go from being above 1 to less than 1, and now your output voltage would be less, but your output current would be more. So by just changing the way you hook it up, or by changing the number of windings, you can take any arbitrary input voltage and make it any arbitrary output voltage. The only catch is that the current is going to do the opposite so that the powers are equal. Does that make sense?
So it's as long as the ratio stays the same. So that those are the ratio of n. So if you basically flip this one, then you would have to do the greater coils over the lesser coils to get your ratio of n.
It's always the output.
Okay, so
over the input.
So it would still be the output over the input, so n2 over n1. But then you would have to make sure that number now is going to be less than 1.
Bingo.
Decimal.
That's it.
So to make sure it stays the same, you flip the way you do the I and the V. You do ni1 and then 1 over n v1.
Oh no. All the equations stay the exact same.
Right.
Let me just redraw it. Let me draw that for you so it's a little clearer what I'm talking about. If you flip this thing around, you still got V1 on the input. The only difference is now you've got all these windings on the input, and you've just got a couple on the output. But all the equations stay the exact same. Still, if you've got I1 over here, you still have I2 equals 1 over n I1. And you still have V2 equals n times V1.
So now isn't n going to be a decimal number, less than 1?
This is still, you're still going to call your input, that's right, Dom. You'll still call your input winding N1, your output winding N2. Now you've just flipped the numbers for N1 and N2. So you're still going to define N to be the ratio of your secondary over your primary coils. But in this above example, N might be equal to 2, and in this example, N might be equal to 1/2. So now your output voltage is less than your input, your output current is greater than your input. But the rules that I gave you are always true, regardless of what N is. You could even make N 1 if you wanted to. And then your input voltage will match your output voltage, and your output current will match your input current.
So if N is 1, then that means that those two are going to have the same number of coils, which means it wouldn't even really be a transformer, would it? Or would it?
That is a really subtle question, Dom. So I haven't yet gotten to the part that I really want to talk about, but you just raised, that's just such a good question that I'm going to draw that. And we'll see what happens. So first of all, if N1 is on both sides, so therefore N equals 1, then that just means that this will be V1 over here, and that just means that this will be I1, and it doesn't seem like you've changed anything, right?
Right.
But watch this. Maybe I want to put ground over here. And now relative to ground, this point is exactly V1.
Mhm.
But maybe I want to put ground up here. And now, relative to ground, this is minus V1. And so I've just inverted my phases by 180 degrees, which I could not do otherwise. In other words, although these voltages are the same, the voltage differences between these two wires are the same, and the currents are the same, these two circuits are completely electrically isolated from each other. There is no way to get electrons running around in here over to this side. And so you can do tricks like putting ground over here, and now you can get fancy about the ways you can connect them, and you can actually double your voltage or invert it or do all kinds of other neat tricks like that. What probably doesn't make sense to you quite yet is why you would make a circuit like that. We'll cover that shortly.